All right, this will be my second video on kind of looking at basic probabilities. So I'm gonna look at a little bit more things that require graphics to go with it. So the age distribution of a population is shown. So we have this pie here that's showing age distribution. So 5 to 14-year-olds is 13% of them. 15 to 24 is 14. 25 to 34-year-olds, 13% of them. 35 to 44 years old, 13% of them. You get the idea. So we need to find the probability of each event below. So the first thing we're going to do is we're going to find a person is chosen at random, or a person chosen at random is from 25 to 44 years old. So we need to find the probability that they're 25 to 44. Well, I'm a little bit of a visual person, so what I'm going to do is I'm going to use my pen here and kind of look at, well, what pieces of this pie all apply to this 25 to 44. So I have age 5 to under 5, no. 5 to 14, no. 15 to 24, nope, that's not quite it. 25 to 34, that's part of what I need there, so I'm going to need this piece. 35 to 44, that's also between 25 to 44. 45 to 54, 55 to 64, 65 plus. So I need both of those pieces. So if I need both of those pieces, we're looking at this part right there, which is I have 0.13 plus 0.13, which that ends up being 0.26 or 26% is the probability that you randomly select one person and they're from 25 to 44. All right, so that's nice. Let's get a little bit more complex here. So my next one, a person is chosen at random. A person chosen at random is at least 15. So we're looking at the probability that they're at least 15. So I need to think in my head, what does that even mean, at least 15? So you're going to kind of have to rely on a little bit of English there. When you want at least 15, that means the lowest amount can be 15. So anything 15 or above. So I'm going to use my blue pen here, and let's kind of look at what is anything 15 or above. So I have under 5, no. 5 to 14, no. 15 to 24, so I need this piece. 25 to 34, that's at least 15. 35 to 44, that's at least 15. 45 to 54, that's at least 15. 55, 64, and 65 plus. So I'm using all those pieces. 1, 2, 3, 4, 5, 6. 6 different pieces there. Now the issue with that is that's a lot to add up. So I could, if I wanted to answer this question, take 14, 13, 13, 15, 12, and 13 and add those all up. That's totally fine. But sometimes with probability, there is shortcuts there. And it's on the basis of the idea of, well, I know all probabilities of everything is going to add up to 1 or 100%. So this entire little pie chart here is all going to add up to 1. Notice how I'm using 1, 2, 3, 4, 5, 6 pieces. But notice what I'm not using. I'm not using this piece or this piece. That's what I'm not using. And the way we can use that to our advantage is we use something called the complement. The complement. And what that means is if you want to know the probability of some event not happening, that's 1 minus the probability of that event. So if I want to know the probability that they're at least 15, well, maybe if I want to do that, let's figure out 1 minus the probability they're not at least 15. So let's look at the probability that they're not at least 15. So the original question was I wanted the probability that they are at least 15, which is all those. Well, what pieces correspond to being not at least 15? Well, that's just these two. That's less to add up. So I have a 7% and a 13%. So if I want to know the probability that they're not at least 15, that's just 0.07 plus 0.13, which ends up being 0.20. So again, with the idea that all of this must add up to 1 or 100%, if I subtract off the pieces I'm not using, so if I took both these pieces away, what would I be left with? All the pieces I originally wanted. So if I take 1 minus this top, I should be left with everything I originally wanted to answer this question. So if I do 1 minus 0.20, I'm going to get 0.80, which is 80% chance that you pick one person at random and they are at least 15 years old. So this is an idea of using the complement. As we go on, this becomes a little bit more complex. So if they ask you a question like, well, what's the probability that someone's at least 15 years old? You could answer that by doing 1 minus the probability that they're not at least 15. If I want to know, hey, what's the probability of rolling 6? Well, subtract it from what's 1 minus the probability of not rolling a 6. So it's almost kind of opposites there will allow you to get there. If this was not, then this would be, so if I said what's the probability of not at least 15, that's the same as 1 minus the probability that they are at least 15. Notice how these are opposites, which makes them complements. So we got 0.80 or 80%. We would have still gotten the same thing if you would have taken 0.13 plus 0.12, 0.15 plus 0.13 plus 0.13 plus 0.14. So you would have gotten 80 if you would have added those up too. I just wanted to show you the idea of a complement. On the back, we have one more idea I want to talk about. So we're going to roll a 6-sided die, but we're going to roll it 60 times. The table below shows the results. So I rolled a 1, 11 times, a 2, 14 times, a 3, 7 times, a 4, 10 times, 5, 6, 12. So I rolled a die 60 times, that's what I got. They want to know for which number is the experimental probability of rolling the number the same as the theoretical probability. So we're dealing with this idea of experimental probability. Now what that is it's entirely based on trials. So this is based on trials, based on what happened. So let's look at it. If I rolled a 1, how did that play out? Well, it happened 11 times out of a total of 60 times. So the experimental probability, based on trials, it happened 11 out of 60 times. Well, let's look at 2. Well, that happened 14 out of 60 times. And you can probably kind of see the trend here. So I'm going to calculate all of these experimental probabilities. How did 3 happen? Well, it happened 7 out of 60. A 4 happened 10 out of 60. A 5 happened 6 out of 60. And a 6 happened 12 out of 60. So these are all experimental probabilities because it's based on the trials, what actually happened. They want to know for which of the numbers is the experimental probability for rolling the number the same, that means equal to, the theoretical probability. Now, theoretical probability is all just kind of like a, well, what if? So if you're rolling, we're going to assume it's a fair 6-sided dice. What should happen if you roll that dice? What's the chance that you roll a 1? Well, how many times can you get a 1? Well, once. Out of how many total different ways? Well, there's 6 total outcomes, so the theoretical probability is a 1 in 6 chance of rolling a 1. Now, moving on to 2. What's the chance that you roll a 2? Well, you can roll a 2 one way out of 6 times. Well, 3 is going to be 1 out of 6. A 4, you have a 1 in 6 chance. A 5, a 1 in 6 chance. And a 6, a 1 in 6 chance. So they want to know for which number, so which die roll, 1, 2, 3, 4, 5, 6, when do we ever get the same experimental probability and theoretical probability? Now, I don't know about you. I'm not really sure which of these fractions match up or which of these are matching up. So what I'm going to do is I'm going to calculate, use a calculator and calculate quickly what these decimals are and see if they match up. So 11 out of 60 is 0.183. Down here, 1/6 is 0.166, so on and so forth. Those are not the same. So then let's move to 2. 14 out of 60 is a 0.233. 1 out of 6 is a 0.166 still. So it's not a 2. Move on to 3. 7 out of 60 is 0.116. Rolling a 1 out of 6 is 0.166 still. Move on to the next one. 10 out of 60 is 0.166. And 1 out of 6 down here is 0.166. So it matches up for those two. So I know a 4 it's going to work, and I wrote that down on the bottom. But let's continue checking because it might be for more than one. 6 out of 60 is 0.1. 1 out of 6 is 0.166. Those aren't the same. 12 out of 60 is 0.2. 1 out of 6 is 0.166. Those don't match up. So the only time the theoretical and the experimental probability match up is rolling a 4. And that was probability 2.